Okay, so today is a lesson on acid dissociation problems. So we're going to tie back into the concept of Ka that we looked at in the last lesson. And we're going to look at something called percent ionization. And we're going to solve these problems using the ICE tables that we learned about in the last unit. So I don't think you'll find these too difficult because it's very similar to some of those equilibrium problems that you've done before. So let's take a look at the first type and we'll just work through a couple examples to get the hang of it. So this would be, this type of problem, we'll call it type 1, is finding the percentage, finding the concentration of the hydrogen ion and the percent ionization when you know what the Ka value is. Okay, so this says find the find the concentration of the hydrogen ion and the percent dissociation of a 0.5 mole per liter hydrofluoric acid solution. Okay, so first of all, this percent dissociation or percent ionization, really what it means is the percentage of the acid that actually dissociates or breaks up into its separate ions. So we know strong acids basically completely ionize. They completely dissociate into their separate ions. But as you go down your Ka chart of acids, the acids get weaker and weaker. So as you go down, less and less of the acid dissociates. So hydrofluoric acid, it's not a strong acid. It's about, I don't know, a third of the way down the Ka chart. Okay, so imagine you have a beaker. Whoops. Here's your beaker, and here's in it the hydrofluoric acid solution. So hydrofluoric acid dissolved in water. You're going to have some molecules of just the HF that stay intact. And then you're going to have some that break, some ions, right? So some ions floating around amongst some that have stayed together, okay? Because it's not going to completely dissociate. It's just going to partially dissociate. So when you're calculating this percent ionization, you're calculating what percentage of the acid is actually in this ion form amongst this solution. Okay, and then the Ka we're going to pull from our chart, and we're going to use that Ka to find out, well, what's the concentration in this solution of the hydrogen ion, because we know that there's also the fluoride ion would have a concentration and the hydrofluoric acid would have a concentration. Okay, so here are the steps. Instead of reading through the steps, let's just do the steps in relationship to this, this question. So it says, write the acid dissociation equation first. Okay, so we've got that actually already written here. Hydrofluoric acid breaks up into the hydrogen ion and the fluoride ion. Now, if you go to your Ka chart, the reaction is shown as HF plus H2O. So it doesn't show aqueous and whatever, but I'm going to add that in. Plus H2O, which is a liquid. And that you would take this hydrogen from the hydrofluoric acid and it would jump on here to the water to make H3O plus, and that would leave this as just the fluoride ion. Okay, and that's written on your Ka chart. Okay, so that is one way to express that, but when you're just writing it for, like, you can just simplify it into this, like just break the hydrofluoric acid up into the two separate ions for these purposes. Okay, so we know if we zip back up to the question, it says find the hydrogen ion concentration and the percent dissociation of a 0.5 mole per liter solution of hydrofluoric acid. So that means we have a 0.5 mole per liter concentration to start with, okay, and our concentrations of the ions initially would be 0, right? Before they've actually separated, they would have a concentration of 0. So we're going to use X, just like we did in the past, to represent the change in concentration. So the concentration of the hydrofluoric acid, or whatever your reactant happens to be, is going to decrease. So we're going to go negative X, whereas the concentrations of your products are going to increase as the reaction proceeds. So we're going to say plus X for both of those. So then these guys just become X, and this one becomes 0.5 minus X. Now, just like we did in those common ion questions from the equilibrium unit, we were able to ignore this, okay? Now, the reason for that is going to be that in this particular situation, this X value would be extremely small. Okay, so up here it says because the hydrogen ion concentration is small compared to the hydrofluoric acid concentration, we can ignore the X in that equilibrium concentration for HF. So we're just going to leave that out when we do our calculations. It simplifies the calculation, and it would make very, very little difference to your end result. So it's not necessary to include. So let's just put a little note there. We will ignore X in the calculation. Okay, so our Ka expression, just like any calculation for K, KEQ, KW, any of the ones that we've done, we take our concentration of the products. So we've got these two guys like this, divided by the concentration of the reactants, or reactant in this case. Okay, now what can we do with this is we can plug all of these things in for the various concentrations, and we can also get a value for Ka from our Ka chart, and that will allow us to solve for X. So let's just flip back to the Ka chart. Okay, so I'm going to show you hydrofluoric acid. So this is that original equation I wrote out. That's how it's always going to be expressed on this chart. And if you zip across to the far side, it gives you the Ka value. So 6.7 times 10 to the negative 4. So I'm going to use that, and I'm going to put that in here. 6.7 times 10 to the negative 4. And just to remind ourselves where that came from, let's just put from Ka chart. So when you're looking back, you don't think, where did I get that number from? Okay, now each of these can be represented by X, and I'm simplifying the equilibrium concentration of hydrofluoric acid to just be 0.5. Okay. So what I can do to solve here is I can multiply 0.5 times the 6.7 times 10 to the negative 4. So that would give me 3.85 times 10 to the negative 4 equals, so this is no longer here because I've multiplied it over here. So I'm left with x squared on this side. So to solve for x, I'm going to take the square root on both sides to get x is equal to 0.0183. So what does that mean? Well, x, I was originally asked two things. The first being find the hydrogen ion concentration. Okay, so x happens to represent the hydrogen ion concentration at equilibrium. So that is what we're looking for. So let's say, therefore, the hydrogen ion concentration is equal to 0.018 moles per liter. All right, so let's flip to the next page to do the next part, which is percent ionization. Now, if you look back in your steps, I'll just flip back to that for a second, the percent ionization can be calculated by taking the concentration of the hydrogen ion at equilibrium. We want to look at it at equilibrium because initially it would not have any concentration. And we want to compare that to the initial acid concentration, like the concentration of the acid that we started with. So we're trying to find out how much of this is there floating in amongst these guys. How does it compare to the concentration of the acid? Okay, and then we multiply by 100% to get it as a percentage. So we're going to take the percent, or sorry, not percent, why do I keep saying that? The hydrogen ion concentration, and I'm just going to put EQ here at equilibrium, divided by the hydrofluoric acid concentration, and I'll put an I for initial, times 100%. So I'm going to plug in those values. So this will be what I just calculated, 0.018. I'll just include the other decimal place. And initially, the hydrofluoric acid concentration, so this will be what was given in the question, is 0.5. Okay, so that equals 3.7%. Okay, so a fairly small percentage, but you'll see as we go down, like our next example is H2O2, hydrogen peroxide. It's even further down the chart. So it's an even weaker acid than hydrofluoric acid. You'll see its percent ionization is much, much lower than even this. So this says how to check to see if our assumption is okay. And our assumption being, was it okay to leave out that X in the hydrofluoric acid concentration at equilibrium? Remember, we just simplified it to 0.5. We took off the minus X. So the 5% rule just means that if you end up getting a value for your percent ionization that's less than 5%, that's telling you if it's less than 5%, then that means that hydrogen ion concentration is quite low. Therefore, that X value is really insignificant in the calculation. So as long as it's lower than 5%, it's okay to leave that X out. So let's just say if the percent ionization is less than 5%, we can safely ignore the X in the hydrofluoric acid concentration, we'll say at equilibrium. Okay, so let's try another one. This time we'll be able to compare how this weaker acid compares to one that's a little bit stronger in terms of ionization. So we're finding the same two things, the concentration of the hydrogen ion and the percent ionization. we're starting with a 0.75 mole per liter solution, and this is hydrogen peroxide. So I'm going to show a simplified dissociation of hydrogen peroxide. Okay, so remember it's only going to lose one hydrogen ion at a time. Okay, so one of your products is going to be H+. Okay, to get the other product, it's going to be, this is just going to drop by one hydrogen. Okay, so it's instead of H2O2, it's going to be HO2, and that's going to end up with an overall negative charge because you've lost one positive ion. However, you can always check your Ka chart. So let's just find hydrogen peroxide is here. So you can always check over here to see the products. Remember, we can always substitute out the hydronium ion for the hydrogen ion. So in these cases, we do that just for simplification purposes. And then your other ion, technically your conjugate base, is the HO2 negative. So if you're unsure of what to put for the product, you can always refer to this chart to come up with your products. All right, so we're going to make our ice table. So H2O2, H+, and HO2 negative. Okay, so we're starting with 0.75 for a concentration of hydrogen peroxide, and our products would start at 0. Our change, we're going to use minus X for the reactant and plus X for the products. Okay, so these guys become just X, and this would be 0.75 minus X. But again, we're going to just leave that out, and it's pretty safe to bet that that's going to be just fine, especially with like hydrogen peroxide's pretty close to the bottom of a chart, so it's quite a weak acid. So therefore, we can expect a very low percent ionization, right? The weaker the acid, the less it ionizes or dissociates. So this X value is going to be extremely small. The hydrogen ion concentration in solution is going to be very, very small. Therefore, we can safely leave that out, but we'll always double check at the end that that was okay to do. I'm just going to tidy this up a little bit. Okay, so Ka then is equal to H+ times HO2 negative divided by the concentration of H2O2. Now remember, we can pull the Ka value from the chart, so let's do that. And here's hydrogen peroxide. If we read over, it's 2.4 times 10 to the negative 12. So let's fill that in. 2.4 times 10 to the negative 12. We've got X, and we're simplifying this to 0.75. So I'm going to multiply across to get rid of my fraction. That will give me 1.8 times 10 to the negative 12 equals X squared. Then I'm going to take the square root to solve for X. So X then equals 1.34 times 10 to the negative 6. So I'm just going to say, therefore, the hydrogen ion concentration at equilibrium is 1.34 times 10 to the negative 6 moles per liter. Okay, so that's the first part of the question solved. The second part is the percent ionization. So now that I know that this is the concentration of the hydrogen ion, I can compare that to the concentration of the acid, and that will tell me how much ionized, what percentage of the hydrogen peroxide actually broke up into ions. or dissociated. So I'm going to take this, the hydrogen ion concentration at equilibrium, and I'm going to divide it by the hydrogen peroxide concentration initially and multiply by 100 to make a percentage. So 1.34, so I'm using the value I just calculated, times 10 to the negative 6, divided by 0.75 times 100 is equal to 1.8 times 10 to the negative 4%. So an extremely small percentage. So you can see that's significantly less of the acid ionizes compared to hydrofluoric acid, which was not considered a strong acid, but much, much stronger than this one, close to the bottom of the chart. So a very, very, very small amount actually breaks up into ions. Well, let's just do that. Okay, and because this is significantly less than 5%, we're safe to eliminate that X earlier in our calculation. Okay, let's try another type. So type 2, this is just, we're now going to calculate Ka. So we can always pull Ka from our chart, but sometimes you're given concentrations and asked to calculate Ka. When you get your answer, you can always compare it to the chart, and it should be very, very close to the value on the chart. So we're given that we have a 0.1 mole per liter solution of acetic acid. We know that it only partly dissociates because it's not a strong acid. So the hydronium ion concentration at equilibrium is 1.34 times 10 to the negative 3 moles per liter. What is Ka for this acid, and what's the percent ionization? So here we're given, okay, so this is the acetic acid dissolved in water breaking up into the hydronium ion and the acetate ion. So this is what you would see on your Ka chart written out. We're told that the acetic acid has a concentration of 0.1. Remember, we're not going to factor the water in because it's a liquid, right? So its concentration is constant. So we'll see that our products start with a concentration of 0. So we've done problems like this before in the equilibrium unit. So if you know that this is the equilibrium concentration of the hydronium ion, then the change here is plus 1.34 times 10 to the negative 3. Now, as long as you have a 1-to-1 ratio throughout your balanced equation, which in all of these situations you will, then this one will also be plus 1.34 times 10 to the negative 3, because they're a 1-to-1 ratio. So this is the same value. And we know the concentration of our reactant will decrease, and again, it's still a 1-to-1 ratio, so it will decrease by this amount. So we're just going to subtract this from 0.1. When you do that, what you get is 0.0.09866. Okay, so we now have everything we need to calculate Ka. So Ka is going to be our product's concentration multiplied divided by our reactant concentration. We're not including water because it's a liquid. Okay, so I'm going to put in here 1.34 in brackets times 10 to the negative 3. You can either say squared or just write it out again. and I'm going to divide by the concentration of the acetic acid at equilibrium. So when I do that, multiply and then divide, I get 1.82 times 10 to the negative 5. Now, because it's a constant, it doesn't have any units. Just to make sure that we've done our calculations correctly, let's just look at the Ka chart for acetic acid. So here's acetic acid, and you'll see its Ka on the chart is 1.8 times 10 to the negative 5. So we're good. It may vary just the slightest bit, but it should be like only off by, say, like a decimal place or whatever. Okay, now we're gonna calculate the percent ionization. We could have done this initially because we had everything we needed, but we'll do it here. Okay, so I'm gonna take the hydronium ion concentration at equilibrium, and I'm gonna compare it to the initial concentration of the acetic acid, right? Because you can't use the initial concentration of this because there was 0. So we want to see how much ionizes, so at equilibrium, how much of this ion exists compared to the original concentration of the acid. So let's plug that in. So this is we were told this in the question. And we were also told that the initial concentration was 0.1 mole per liter of the acid. So that works out to a 1.3% ionization. So I'm just going to write out what that actually means. You don't have to include this at the end, but just so you know. So this means that 1.3% of the acetic acid molecules are ionized at one time. And the reason I say at one time is because this is a reversible reaction, right? And it reaches an equilibrium. So once that equilibrium is reached, the forward and reverse reactions are still both occurring. They're just occurring at the same rate. So you'll never have more than 1.3% of the solution ionized, but it will be like fluctuating in and out of that ionized state, right? Some will be forming back into the acetic acid simultaneously while this is breaking apart into its separate ions. Okay, so we'll end by just doing one more, and then you should be able to try some on your own at that point. So this one says, calculate Ka and the percent ionization for a 0.1 mole per liter solution of hydrofluoric acid if the hydrogen ion concentration is 7.8 times 10 to the negative 3 mole per liter in the solution. So you can always sort of tell what you need to do in terms of your dissociation equation based on what the question asks. So in the previous one, it referred to the hydronium ion, so that's how we wrote it. Generally, the questions refer to the hydrogen ion. So if they're referring to the hydrogen ion, we can do the simplified dissociation. So I'm just going to say hydrofluoric acid, and I'll show that it breaks up into hydrogen and fluoride. Okay, so I'll make my ice table. Okay, so initially I've got 0.1 here. These guys would be at 0. And I'm told that the hydrogen ion concentration at equilibrium would be 7.8 times 10 to the negative 3. Okay, so I should have done this. There we go. Maybe I can write a little neater. So this just means we're going to go plus 7.8 times 10 to the negative 3 for both of these. This is all a 1-to-1 ratio. And this one would be minus. Okay, so this becomes just the 7.8 times 10 to the negative 3. This you'd go 0.1, subtract that value, and that equals 0.0922. So now we can calculate Ka. So this is the expression. So I'm just going to plug in my values. So I've got 7.8 times 10 to the negative 3, either, excuse me, squared or write it out twice. And HF was 0.0922. So if I multiply and then divide, what I get is 6.60 times 10 to the negative 4 for my Ka value. So let's just pop back to our chart and compare that. Make sure we're doing this, calculated it correctly. So hydrofluoric acid says 6.7 times 10 to the negative 4. So we're right in the correct ballpark. We're just off by 0.1. So that could simply be the number of decimal places our concentrations were initially rounded to. We're definitely, that would be close enough to know that you're doing it correctly. Okay, and finally, percent ionization. I'm going to take the H plus concentration at equilibrium, and I'm going to divide by the initial concentration of the acid. So this is 7.8 times 10 to the negative 3. And initially we had a 0.1 mole per liter solution. So this equals 7.8%. Okay, so that's again just telling you that at any one point in time, 7.8% of the hydrofluoric acid molecules are ionized. All right, so you guys can work on worksheet number 9. So there'll be questions similar to what we just did to practice this.